Okay, so welcome back. This is a discussion session or a Q&A with my two sons and two-star pupils, Robert and Gabriel. And so let's just go ahead and begin. We're going to be talking about kinematics in 1D. So describe as many situations as you can where the average velocity is different from the average speed. When would the average velocity be different than the average speed? So what directions can you go? Because
Forward and backwards.
Okay.
Oh, if we're going backwards, we can't. That would be a negative velocity, I believe, but not a negative speed.
Sure, that's right. So if you're going in the negative direction, then your velocity would be negative, whereas your speed would always be positive, of course.
Yep.
Any other situations where you might have a difference in the average velocity than the average speed? Now let's take a situation. What if I drive at a constant velocity
I know
from
one.
what?
Okay. If you drive to one place and then back at let's say 60 miles per hour, the average velocity would be different than the average speed.
Yeah, if you make a trip forwards and then back again, right, your average speed will be the sum of the speeds over the two paths, whereas the average velocity in this case would be 0.
Yes.
All right, number 2. Is it possible for the instantaneous velocity to ever be less than the average velocity? Can the instantaneous velocity be less than the average velocity?
What's instantaneous velocity?
That's the average. That's what you'd like, for example, read out on your speedometer. It tells you how fast you're going right now, whereas an average velocity is over some time interval.
I suppose.
Yeah.
Sure. Yes.
What about greater than? Is it possible for the instantaneous velocity to be greater than? Let's say my average velocity was 50 meters per second, and my instantaneous velocity, could it be 100 meters per second?
Yes, it can be quick at 1 second and slow down later.
Yes, exactly. So it can be,
Exactly.
yeah, yes in both cases. Very good. Question number 3. Is it possible for the average velocity to ever be greater than the largest instantaneous velocity? So let's say we're driving our car in a straight line, and we find that for this long trip that we take, that our average velocity was 60 miles per hour, okay?
All right.
But let's say, I said that wrong. Let's say that over the course of this long trip, at some point along the way, I get up to, say, 75 miles per hour, okay?
All right.
So is it ever possible for the average velocity to be greater than the largest instantaneous velocity? So if the fastest I ever went was, what did I say, 70 miles per hour? 70 miles per hour. Is it possible that my average velocity is 100 miles per hour?
No.
No. It will always be between the minimum and maximum velocities, okay?
Yes, it could be the same or less.
It is an average after all, right?
Yeah, same or less.
All right, number 4. Is it ever possible for a particle with non-zero average speed and 0 average velocity to experience acceleration? That's a kind of a tough, wordy one. You have to think about what it's saying, right? Is it ever possible for a particle, so in this case just some particle, with non-zero average speed, okay, so it's got some distance per time that it's actually traveling, but its average velocity is 0, okay? So it could be that case where we took a trip and then returned back to the starting point, so our displacement was 0, right? Is it possible, is it ever possible, for that particle in this circumstance to never experience acceleration? Could you do that without experiencing acceleration?
No.
What do you think, Rob?
Good.
All right. So it does not have a 0 speed. So the speed cannot
There's a
be.
non-zero speed, that's right.
Okay,
Some
so-
positive, well, it's always positive, but some speed. It's not 0.
All right. And it's, what did you say about velocity? Its velocity is 0.
It has a 0 average velocity, which means the total displacement divided by the time interval in question is equal to 0.
And you were asking us whether it can have acceleration.
I'm asking if it, is it possible for in this situation for it never to experience acceleration?
Aye.
So if it never experiences acceleration, that means it's got to be traveling at a constant velocity. If we're traveling at a constant velocity, can we also have a 0 average velocity?
No, I don't think that's possible.
No, it's not, right? So any loop or circuit will have a non-zero average speed and a 0 average velocity.
Because
So in 1D, a round trip satisfies this.
Because acceleration has to have a change in velocity.
And yes, in this case, it's a change in the direction that's causing the change in velocity. That's the acceleration. Exactly. All right, number 5. If the average velocity is 0 during some time interval, must the instantaneous velocity be 0 at some point during this interval? What about the speed? And you can support your answers with a sketch of position versus time.
Could you repeat that?
If the average velocity is 0 during some time interval, must the instantaneous velocity be 0 at some point during the interval? So the average velocity is 0.
Yes, it must be.
Yes, it must be. So a good example would be if I take a ball and I throw it straight up,
Yeah.
right?
It'll,
And track how long it takes to go, once it leaves my hand until it goes up in the air. It will stop, right? It's under the constant acceleration of gravity. Reverse direction, land in my hand again. The displacement is 0 because it's back where it started, right? But it had that point at the top of its path where it stopped and then reverse direction. So it has to be 0 somewhere.
yeah.
All right, question number 6. If the instantaneous velocity is always constant, can the average velocity during different intervals ever be different? So if the instantaneous velocity is always constant, can the average velocity during different intervals ever be different?
No.
I agree.
Yeah, no. If the instantaneous velocity is uniform, then the position function will be a single line. Since the slope of a line does not vary, the average velocity which is computed from points on this line will always be equal to the instantaneous velocity. All right, number 7. Give an example of motion in which the velocity is negative, but the acceleration is positive.
Example of motion.
And you can support your answer with a sketch of velocity versus time if you want. Example of motion in which velocity is negative, but the acceleration is positive.
Example of motion where the what is negative?
The velocity is negative.
All right, but the
So I'm
acceleration is
traveling at, 10 meters per second, negative 10 meters per second. But the acceleration is positive.
You wouldn't call accelerating backwards negative acceleration, would you?
Well, yes, you would if you're accelerating in the negative. If there's an acceleration in the negative direction. Some people call it deceleration.
But let's just call it
Yeah.
acceleration.
But in this case, we have a positive acceleration. So the acceleration is in what we're defining as the positive direction, but our velocity is in the opposite direction. We're in 1D. So,
Well, I don't see how that can be possible.
well, think about it.
If you
If we're traveling in, say, this direction,
Yes?
right? And we call that the negative direction, but the acceleration is in the opposite direction. Now, let me make it easier. Let's say that this is the direction of the acceleration, okay?
All right.
And it's also the direction of the positive direction. So our ruler goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right?
Yes?
But our particle is traveling in the opposite direction, so it has a negative velocity. Any ideas what this would correspond to? What would be a good example of this motion? Now, we don't have a lot of choices with one dimension. So if I take a ball
Yes?
and I toss it in the air, okay?
Right.
But I take my ruler and I set it up such that the 0 is up high,
All right.
right? So it's traveling in the negative direction, right?
Yeah.
So it has a negative velocity, right?
Yes?
Which way is the acceleration going? Well, it's down towards the Earth in the positive direction, right?
Yeah.
Yes?
So that would be an example where you'd have that. So what happens to the object? So if we are traveling in the negative direction but experiencing a positive acceleration,
Yes, you're right.
are we speeding up or slowing down?
Speed up.
We are
Speeding
up.
No.
You say if we have a positive acceleration?
Our acceleration is in the positive direction,
And then
but our velocity is in the negative direction. Are we speeding up or slowing down?
We are...
Throw a ball in the air. Does it speed up as it gets higher, or does it slow down as it gets higher?
It slows
It
down
slows
as it gets
down.
higher.
Yeah, it's slowing down.
Then why did you say
Slows
falling?
down.
Or going
Slows
down?
It's not falling. It's going up, right?
Yes?
It's traveling in the negative direction.
All right.
At some point, it's going to stop entirely, right? Once it slows down to a 0 velocity, and then it's going to reverse direction. Now it'll have a positive velocity and a positive acceleration, okay?
Okay.
And that, of course, is kind of, well, not really. The next question is, give an example of motion in which the velocity and acceleration are both negative.
Acceleration. So that would be going slower and slower in the negative direction?
Well, the acceleration is negative, and the velocity is negative. So if the acceleration is in the same direction as your velocity, what's going to happen to you?
if you drop a ball
Yeah, if I drop a ball,
down
yeah,
from like a tree, then or tree post, whatever, and the lower down you go, the closer to 0 you go. then would be having a negative acceleration and negative velocity.
Sure. That's right. So if I had my ruler set up, this is all about which way we line up our rulers, right?
Yes.
Yes.
Whether we call something a positive or a negative acceleration really depends on which way we lay our rulers out. So if I lay my ruler out such that 0 is down here and 1 or 2 or whatever is up
Whatever's
higher,
up here.
right, then this is the positive direction and this down would be the negative direction. But if I
Yes.
flip the ruler, I flip the sign.
All right.
Yes.
But what never changes, right, is if I have if the acceleration and the velocity are opposite signs, then that's going to slow down. Whereas if they have the same sign, whether they're both positive or both negative, it will speed up.
All
Okay?
right.
All right, next question. If two people simultaneously drop identical eggs from a tall building, and one egg is observed to hit the ground before the other, is there any reasonable explanation for this?
No,
What about you, Gabe?
they hit it at the same time.
It's the same egg, dropped from exactly the same distance, and released at exactly the same time.
Assuming there's no wind and they're
Well, if we observe that they did not hit the ground at the same time, then we might suspect there was a little bit of wind that hit one of them along the way. That's one explanation. Any others? Go ahead.
That, well, I mean, if eggs have this shape, so if you drop it, so maybe if you drop the egg one way and then you turn it around the same egg another way, it could drop at different speeds.
I see. So you're saying maybe one of them was falling with a different orientation,
Yes.
and so the air resistance that it experienced was different. That's a possible explanation. But let's assume that they were dropped identically in the same way, so that what faced
Alright.
the air, what the air resistance was the same for both, all the way down. No? Any ideas?
and the ground was at the same point.
Yeah.
All right. That would
Yeah, that
cause-
means that's dropped from the same height, I guess.
I don't
Yeah.
see how they could hit at a different time. They're the
the-
same weight. They're exactly the same.
What about the ruler?
Same position.
Is it
Everything.
the same direction for
Oh yeah.
everything?
Oh yeah.
Okay.
Everything about them is the same.
Yeah.
So that I don't see it.
Did
No,
somebody
I
push?
don't. I don't think
the
that's
person
possible.
who dropped the
It doesn't
egg
sound possible.
dropped it out.
Yeah, they gave it an initial velocity.
Yeah,
Yeah, if you give it a little initial velocity when you drop it, then it's got, some initial velocity plus the velocity that it acquires during the fall, so it's going to get to the ground first.
Exactly.
That's the answer I was looking for. Let's see. Next question. The apex of a model rocket's flight is the highest altitude attained by the rocket. What is the velocity, speed, and acceleration at the apex? So that's the highest point that the rocket goes
Speed
up.
zero, velocity
Zero.
What about the acceleration?
Well, the acceleration.
The
Well, It's not
acceleration.
accelerating because it's going to stop and then fall back down.
But is it accelerating? Isn't there still the acceleration due to gravity?
At the
You're right.
highest point.
There is.
Yeah, even though the velocity is 0, there's still that acceleration. Okay, because the acceleration is the change in the velocity during a time interval. Okay,
Yes.
and so that on Earth is about 10 meters per second. So yeah, so the acceleration is still just g, as we call it, little g, but the velocity and speed are 0. Let's see here. For an object traveling at a constant velocity, the slope of the position function, x of t, gives which quantity? Average speed, average velocity, or average acceleration? I can draw a picture if you want me to, but
Yeah.
Yes.
it's just a line, right?
Please do.
So-
Picture.
We have x of t on the vertical axis,
Yep.
and t on the horizontal axis. And let's say we've got a nice line like this, okay?
Yep.
So, where'd my question go? Oh, there it is. The slope of the position function, x of t, gives which quantity? So the slope would be the rise over the run. So you could pick a point, say here, and pick another point way down here, right?
Yep.
So that this distance here, right, and this distance here are the relevant quantities, right? This is the rise, this is the run, right?
Yeah.
Obviously the y-intercept is 0, so we'd have x of t equals m, the slope, times t, I almost wrote x, times t plus the y-intercept, which is 0, right? So what is that slope, rise over run? what are the units on the slope? What is the slope measure? What is the rise measuring? What is the run measuring? What's the ratio of
Rise
those two?
is
X to T. Run is
and
T.
Well, it's this x position minus this x position. What do we call that? Maybe if I chose a different point to get this slope from, right? What if instead of choosing these, I said, how about we choose these 2 points? So I've got this and I've got this, right? So the rise, right, would be this x, whoops. We have x of t here. This would be, we'll call it x naught. So this distance here, the rise, is x of t minus x naught. And then here, we'll call this t naught. And we'll call this point here t. So this distance here is t minus t naught. All right?
All right.
This we call delta x, the change in x. This we call delta t, the change in t.
All right.
And the slope is delta x divided by delta t. What's that? Delta x divided by displacement divided by time interval. What is that?
Time. That sounds like. Is that velocity?
It is velocity. It's the average velocity. Okay?
All right.
All right. Next question. True or false? And you have to support your answer with an explanation. The equation x of t equals x naught plus vt, I'll write it on the board. This equation, x equals x naught plus v naught t plus 1/2 a t squared. The question is it true that this equation holds for all motion in 1D?
Is it true?
Is it true for all motions in one dimension?
Yes.
You think yes? What do you think?
Wait.
Is it always true?
For
All right. Well, it seems like you guys don't have that one down. The answer is no. This is false. Okay. This is only true for constant acceleration. Okay. And that kind of leads us into the next question. The average velocity over an interval is always equal to the sum of the initial and final velocities divided by 2. Is that true or false? Well, just listen to it. The average velocity over an interval is always equal to the sum of the initial and final velocities divided by 2.
Average velocity. That sounds right. Yes.
Is the average velocity,
Yes.
v sub average, always equal to v naught plus call it b of t divided by 2? Is that always the average velocity?
It looks like it. Yes.
Let me show you a case, okay? Let this be a velocity versus time, okay?
All right.
Now let's assume we have a constant acceleration. That means that our velocity will be increasing linearly. Okay, so I got another line. Now in that case, if I pick 2 points, here and here, right, and I get these 2 velocities, we'll call this V2 and V1, right?
Yes.
Which we could then write in like this, right? V2 plus V1 divided by 2. The average of this will be right in the middle, right? Which will be right here. So in the case of constant acceleration, yes, that's true. The average velocity is equal to the actual mean or average of the two velocities taken at 2 different points, okay?
All right.
yeah.
But what if it was a curve like this instead? Here's our velocity, here's our time. Let's say it starts out kind of slow velocity and then it speeds up really fast. So I pick a point here, I pick a point here, right? The average of this is going to be here, right?
Yes.
But that is not necessarily the average velocity for this, right?
Yes. Yes, that's true.
Yeah. So this is only true in the case of constant acceleration. Let's see. The displacement delta x is always equal to the product of the average velocity and the time interval. Is delta x, erase some of this so we have some room to work.
Keep going.
Is delta x always equal to, how did I phrase it? Just make sure I get the product of the average velocity and the time I guess we call that delta t if you wanted. Is that always true? Okay, no one has any thoughts?
Oh no, I'm pretty sure I have the answer. I may
What's the
as well
answer?
double check. Yes.
Yes, that's the definition of it. The average velocity is defined as the displacement divided by the time taken, right? The time interval.
Yeah.
So this is by definition true, okay?
It has to be.
Alright.
The previous thing I showed you, right, that the average velocity was equal to the sum of two velocities at two different times divided by 2 is not always true. That's only true in the case of constant acceleration. I think that may be the last question. Yes, it is. That was the last question. Okay, I think that went pretty well. I think we fleshed out some of the misunderstandings that we may have had in our understanding of kinematics in one dimension.
Alright.
You feel like you learned something?
Yes.
Good. How about you?
I learned that I'm great.
You learned that you're great. Wonderful. Well, that's an important lesson. All right, thank you for joining us, and that's all we have for this lesson.